All right, so previously we defined trig functions analytically. And this is the way that we did it, is we just said take any point on the coordinate plane, x, y, just an arbitrary point. You can draw a line from the origin to that point, which is essentially just the distance from the origin to that point. And if you drop a perpendicular from that point to the x-axis, then we defined sine theta, or we defined our six trig functions based off of this sort of triangle that's being formed. So in particular, sine theta is equal to the y coordinate divided by the hypotenuse. So y over r. Cosine theta was x over r, and then tangent theta was y over x, and then the reciprocal functions are just the flip-flop of these. But we also, from this, you may have noticed that we can actually just kind of define trig functions. They're sort of being defined relationally within this triangle as like ratios of side lengths of the triangle. So for instance, sine theta, y over r, well, y is really just this length right here, y over r. So it's just this leg of the triangle divided by the hypotenuse. Cosine theta, same thing. It's the x leg of the triangle divided by the hypotenuse. So really, all of these trig functions could be just kind of like broadly defined as ratios or relations within a triangle. In particular, a right triangle. So at this point, we're only working with right triangles exclusively. So what would that look like? Well, if we have our right triangle like this, and maybe we have some angle theta in here. I can label the sides of this triangle relative to theta. So in particular, this side right here, what we might view as being the height of this triangle, it's the side that's opposite theta. The lower leg is the side that is adjacent to theta. And then we keep this as just the hypotenuse. And from this, we can redefine our trig functions just based off of this arbitrary triangle that we have. So sine of theta is equal to the opposite side divided by the hypotenuse, which is exactly what was happening in our analytical case too. Even though we sort of labeled theta differently, here theta, in the analytical case, theta is this whole angle on the outside rather than the angle on the inside of the triangle. But you could call this angle on the inside maybe theta prime. And in that way, yeah, you get this exact same relational definition of the trig functions, that for sine of theta, we're looking at theta prime. Sine of theta is equal to the side that is opposite theta prime divided by the hypotenuse. So sine of theta is y over r, or the opposite side divided by the hypotenuse. So sine of theta in our arbitrary triangle is opposite over hypotenuse. Cosine theta, same idea. In the analytical case, so cosine theta is x over r. Looking at this triangle relative to theta prime, x is the adjacent side, and then r is the hypotenuse. So cosine of theta is adjacent over hypotenuse. And tangent theta then, well, tangent theta is y over x, so the opposite side over the adjacent side. So tangent theta is opposite over adjacent. And yeah, again, the reciprocal functions, it's the exact same thing. So the reciprocal of sine is cosecant. Cosecant would be hypotenuse over opposite. Secant is hypotenuse over adjacent. Cotangent is adjacent over opposite. It's just flip-flopping these. The mnemonic, the really common mnemonic that is used to remember this right here is Soh Cah Toa. Soh Cah Toa. So sine is opposite over hypotenuse. Cosine is adjacent over hypotenuse. Tangent is opposite over adjacent. So that's kind of the mnemonic for remembering that. So from this, what I want to do is we want to lay out some of the ratios for triangles that might be coming up very, very commonly. So in particular, the triangles that come up very commonly are triangles that have, they're right triangles, where they have either a 30-degree angle, a 45-degree angle, or a 60-degree angle. Obviously, if it's a 30-degree angle, there's going to be a 60-degree angle in there, but they're, like, you want to kind of think of them somewhat differently, because these end up just being sort of like, you can think of them as like quick references, essentially, for various triangle ratios. So I'll just kind of go through what those ratios are. I'll explain, without doing it myself, I'll explain how you can derive these, how these are derived. So the first triangle that we'll look at, which is technically kind of two different triangles, but it's two different triangles in one, is the 30, 60, 90 triangle. Let's see, the way I've oriented this must be 60 and this must be 30 degrees. So this is a 30, 60, 90 triangle, which sometimes in some textbooks you might see this listed as a pi over 6, pi over 3, pi over 2 triangle. Not quite as common, even though we use radians more commonly in trig than we use degrees. We usually specify our so-called special triangles in degrees, so 30, 60, 90. And the idea here is, imagine that the hypotenuse is a length of 1. To derive these other two side lengths, you could imagine that if we had started with an equilateral triangle, where each side is length 1, then every angle is 60 degrees. So this this altitude right here is actually an angle bisector. And in an isosceles triangle, an angle bisector from the top angle bisects the bottom as well. So if this original triangle, when it was equilateral, if this side length right here was 1, then this altitude is also a median, and it's cutting this bottom piece in half. So if the original side was 1, then this shorter side is 1/2 in like the half triangle, in the 30, 60, 90 triangle. And then from that, you can just use the Pythagorean theorem to get this last side length, which is √3/2. So that's one special triangle. The other special triangle that we'll look at that comes up a lot, in particular it comes up, these come up when you're looking at the unit circle, but the other one that comes up is a 45, 45, 90 triangle. So the 45, 45, 90 triangle is, again, it's isosceles. Since these two angles are the same, that means that this triangle is isosceles, so these two sides are the same, and we start with the same premise that the hypotenuse is a length of 1. If we wanted to find these two sides, it's again just the Pythagorean theorem. So if you call each of these sides a length of x, then x squared plus x squared equals 1, and you can solve for x from there to find that each of these sides are a length of √2/2. And this is a 45, 45, 90 triangle, or again, maybe a little bit less common, a pi over 4, pi over 4, pi over 2 triangle. Yeah, it's weird. Some textbooks say that. I think 45, 45, 90, 30, 60, 90, those roll off the tongue a little bit easier. So these are our special triangles, and these are, in particular, these are really helpful for us when it comes to trying to list out ratios of triangles that might be formed analytically. So, for example, if we had something like this, where we had some point, and maybe the point is over here. So as usual, I'm going to make my little triangle. And suppose that we are given that theta, which rotates this way. Maybe theta is equal to what? 150 degrees. Or that would be 5 pi over 6. And we want to be able to say, maybe we want to calculate what is the sine of theta. So this is just an example over here. What is the sine of theta? So in other words, we would be saying, what is the sine of 150 degrees? Well, if this angle right here is 150 degrees, that means that this internal angle in here, your theta prime, must be 30 degrees. And since this is a right triangle, then up here, this must be 60 degrees. So this is a 30, 60, 90 triangle. So the side lengths then are given by our special triangle, our special 30, 60, 90 triangle. It's oriented differently than this one. Like if you were to take this and turn it, rotate it clockwise, then you get this triangle right here, 30, 60, 90. And the reason that these triangles are special and useful is because of similarity between triangles. Similar triangles are proportional, meaning we don't even need to know what this point is, this xy point is. We don't need to know how long the hypotenuse is. We don't need to know x. We don't need to know y, because the ratios, which is all that the trig functions are, they're just ratios. The ratios will be the same no matter what. So if you were to like extend this line out and grab any point on that line and make this same triangle, they're not the same. They're not congruent triangles, but they are similar. So their side lengths are proportional. So you could grab any point on this line, and sine theta is always the same thing. That's what I mean by defining trig functions relationally, is that they can be defined just within the triangle. So sine of theta, again, is the opposite side over the hypotenuse. Opposite over hypotenuse. So in this case, sort of the reference angle that we're looking at is 30 degrees. So what is the side that is opposite 30 degrees? It's 1/2. And we've conveniently chosen the hypotenuse to be 1. So 1/2 divided by 1 is just 1/2. So sine of theta here is 1/2. Oops. You've got to be a little bit careful still, because the angle of theta matters. So sine theta 1/2, cool. Yeah, that falls out pretty fast. Cosine of theta, on the other hand, well, same idea. We want to define it relationally. So the cosine of theta is the adjacent side divided by the hypotenuse. The side that would be adjacent to our 30-degree angle is √3/2. Hypotenuse is 1. So the adjacent side divided by the hypotenuse is √3/2. But that doesn't mean that in this case cosine of theta is √3/2. Why not? Well, it goes back to the way that we originally defined all of this, that it was originally defined analytically. So cosine of theta is x over r. So the x coordinate over here, even though we don't know what this coordinate is, we do know that that coordinate would be negative, right? So over here, this x coordinate is negative. The y coordinate is still positive. That's why sine theta is 1/2. But the x coordinate is negative. So all that means is that we grab our relational, the relational ratio, adjacent over hypotenuse, and we just have to account for the fact that, well, this adjacent side would be a negative coordinate. The hypotenuse is still positive. The hypotenuse is always positive. You can essentially, and this is the way that we defined r, was through the Pythagorean theorem. R is the distance from the origin to the point. So r is always positive. The hypotenuse is always positive, but x and y can be negative. And here's a situation where x is negative. So yeah, the reference triangle is helpful in terms of telling us what that ratio is, but you have to be careful. You still have to take into account the angle, because the angle determines whether or not that ratio is positive or negative. So in this case, the x coordinate would be negative, so the ratio is negative. Cosine of theta is negative √3/2. And then tangent theta is opposite over adjacent. So the opposite side is 1/2. The adjacent side is negative √3/2. So in the reference triangle, it's √3/2, but because of the x coordinate, it's negative. So negative √3/2, which evaluates to what? Negative 1/√3. So negative √3/3. I might have done my math there wrong, but the premise is right. Let's see. Yeah, so, and this is, like, when we talk about reference angles, what we mean is this little angle, this acute angle that is formed between the terminal side of your angle theta and the x-axis. So this 30-degree angle in here, even though theta is 150 degrees, we are working with the reference angle of 30 degrees because that tells us which of the special triangles to use. So the reference angle in this case would be 30 degrees. The reference angle would be 30 degrees again if this was, instead of 150 degrees, if it was 30 degrees below this x-axis over here. So if it was 210 degrees, again, you would still be working with a 30-degree reference triangle. But you'd have to take into account, is x positive or negative? Is y positive or negative? So if we were working with this point down here at 210 degrees, again, we're still using the 30, 60, 90 triangle. We can use those ratios, but we have to take into account that both x and y are negative at this point. So all that means is that both sine theta and cosine theta would be negative. Tangent theta, interestingly enough, would be positive. Since it would be a negative over a negative, it becomes positive. Okay, and then the very last thing that comes up around this time is finding angle measures. So suppose that we were given finding angle measures. And what I mean by that is if you're given this kind of a problem, and I'll just write it the really simple way, if sine theta equals 1/2, what is theta? Right? So that's just kind of like broadly what we mean by finding angle measures. It's kind of going in the reverse direction. Rather than being given an angle theta and said, what is sine of theta? We're told sine of theta is 1/2. So what must be theta? That's just what this question is asking. To make it a little bit simpler, and this might not feel like it's making things simpler, but it actually is, because sine is periodic. All these trig functions are periodic. Let's say we'll restrict theta, assume that theta is between 0 and 90 degrees, or between 0 and pi/2. So it's theta is in quadrant 1. So this is essentially saying, in quadrant 1, where is sine of theta equal to 1/2? And for this case, at least, we don't need to use a calculator. If you were using a calculator, you just use the sine inverse button, which is not the same as the reciprocal, by the way. I'll just kind of make this note up here. I think this is a really easy thing to kind of confuse. On the calculator, and just in general, sine inverse of theta is not equal to, actually, I guess I should say, rather than sine inverse of theta, sine inverse of some x. I'll call it x rather than calling it theta, because theta usually represents an angle measure. Sine theta actually takes real numbers as input and outputs angles. So that's why I'm being careful about not using theta there. Sine inverse of x is not equal to 1 over the sine of x. They're different. If you wanted to write this reciprocal, this is the cosecant. So what I'm saying here is that on your calculator, the sine inverse button is not the cosecant button. If you want to use the cosecant button, you could use there's like an x to the -1. That does represent reciprocal. So you could do sine x and then do the reciprocal button, and yeah, that will call out the cosecant. It'll calculate cosecant, or you can write it this way, 1 divided by sine of x. Right. If you did want to write this, by the way, just notationally, what is equal to this in terms of the exponent would be something like this, which it looks weird, and this is why nobody ever writes it. Sine x to the negative 1. This is 1 over sine of x, or 1 over the cosecant. So just be aware of that on your calculator. Okay, so, but if we want to solve for what theta is sine of theta equal to 1/2, if assuming that theta is in the first quadrant, this could be rewritten. This is equivalent. Notationally, this is the equivalent of saying theta equals sine inverse of 1/2. And yeah, you could just pop that into your calculator. And since theta is restricted to the first quadrant, your calculator will give you the right answer. There are times where if theta was restricted to a different quadrant, or if theta was expanded to any angle measure, then your calculator is only giving you part of the story. But these are the same. For me, for whatever reason, I try to really keep this equivalence in mind, just because when you see something like theta equals sine inverse of 1/2, it's easier for me to rewrite it this way, sine of theta equals 1/2, because for me it makes it clearer that it's like, okay, I'm looking for whatever theta makes it so that sine of theta is 1/2. Okay, so yeah, you could toss this into your calculator. You could also recall from our 30, 60, 90 triangle that if this is 30 degrees and it's a 90-degree triangle, the hypotenuse is 1, this opposite side is 1/2, the adjacent side is √3/2, sine is opposite over hypotenuse. So in this case, with the 30-degree triangle, opposite over hypotenuse, 1/2 divided by 1 is 1/2. So it must be the case then that theta equals 30 degrees, or pi over 6. You've got to be careful though, for the reason that if this was expanded, if I said find sine of theta equals 1/2, where 0 is less than or equal to theta is less than or equal to 2 pi. Or in other words, 0 is less than or equal to theta is less than or equal to 360 degrees. So on a full rotation around 360 degrees, where does sine theta equal 1/2? And the answers there are at theta equals pi over 6 and at theta equals 5 pi over 6. Why? Imagine again, we kind of actually looked at this already. Here's my triangle. Assume that this is 30 degrees, this is 60 degrees. We already know from our 30, 60, 90 triangle that the hypotenuse is, if the hypotenuse is 1, this side length is 1/2, and over here this would be negative √3/2. So here's another situation where sine of theta is 1/2, but now theta is not 30 degrees, theta is 5 pi over 6, or 150 degrees. So the answers here are, there are two answers. And if we ask the exact same question, but we said for all possible theta, now there are actually infinite answers, because every single time that theta wraps around and hits either of these 30 or 150 degree coterminal angles, sine of theta is 1/2. So now it would be theta equals pi over 6 plus 2 pi n, or 5 pi over 6 plus 2 pi n, n, where the way that we would write it in more mathy notation is like this, which means where n is an integer. So yeah, this 2 pi n is just adding on 360 degrees every single time. So it's like with this 5 pi over 6, 360 degrees, add 360 degrees onto there, add 2 pi onto there, you end up at that exact same angle. Even though the angle is now, it's not 150 degrees, it'd be what? 510 degrees. Yeah, okay, so that's defining trig functions relationally. That is special triangles, reference angles, and finding angle measures.